Am I audible or not?
Yes, ma'am.
I'm audible. Okay. So why you were absent yesterday? Don't want to answer?
No, ma'am. I went out yesterday, so
Don't miss classes,
Ye-
particularly optical, jab tak is not finished. Okay.
yes, ma'am.
Otherwise, it will be difficult to matlab join intermediate. Na, you will have problems. Okay. What about Vishwaraj? I guess a new name or new login today in the name of Vishwaraj. Okay. So I guess I can start as most of you have joined, it seems. Let's start. So yesterday we left at midway of this particular lecture here, draw the structure of the compounds we left there. Today we are starting from number of geometrical isomers, how to calculate geometrical isomers. Yes, there are formula, though I do not support formula in general, like always you will not have. Usually the type of question which will appear in J will not be directly approachable by formula, but still you should know what is the formula. So just reminding you, this must be in your notes already. The compound has n number of double bond sites and all are capable of showing. Okay, if n, but they are not capable of showing, or some of them are not capable of showing GI, then you have to maintain the n value as only those sites which are capable of showing geometrical isomers, and the molecule cannot be cut into two halves from the center, cannot be cut into two halves. Like, see, here CH3H, so here ET and H. Here corner is CH3, then here corner is bromine. Right? If both sides CH3, then it can be cut into two halves. Exact halves is what I want to use here, or I want to intend here. And from the center, then total number of GI are 2 raised to power n. For example, here only one pi bond capable of GI. So you can say 2 raised to power 1, 2. Here I have two pi bonds which are capable of GI, and it is not symmetrical. Halves means it should be symmetrical both sides. That is what meant here. So 2 raised to power 2, 4. Now here I have 1, 2, 3, 4 pi bonds. But see, this pi bond is not capable of showing GI. Right? So I will use only 2 raised to power 3, 8. That is how you have to use formula. Only those pi bonds which can show GI will be participating in this. Okay. If the compound contains n number of double bonds and it can be cut into two halves, which are symmetrical. Okay. What we want to mean is two identical halves. Like here you can relate the point exactly, right? These are two identical halves. Then there is a different geometrical isomer count formula, 2 raised to power n minus 1 plus 2 raised to power p minus 1. Now this p also varies whether the value of n is even or odd. If it is even, then you can use this p as directly n by 2. If it is odd, then n plus 1 by 2 is what we will use here as value of p. Okay, if the compound contains n number of double bonds and can be cut into two halves, then this formula is to be used. 2 raised to power n minus 1 plus 2 raised to power p minus 1, where p is n by 2 if n ki value is even, n plus 1 by 2 if n ki value is odd. Okay. Now, why this happens? Like I have two pi bonds. If I say 2 raised to power 2, 4 should have been the answer, but why not 4? What happens? So what happens is like both E acceptable, both Z acceptable. But if I have one E and one Z, then EZ or ZE are identical and superimposable. Some of the case are now repeating themselves. So that is why the value is less than what it would have been with 2 raised to power n direct formula. Right? Same here. Same here. Now here again, due to this CL, it cannot be cut into two halves. And it is also not symmetrical. And 2 raised to power 2, 4. So here it will be 4 because this chlorine will not allow EZ, ZE thing being identical. If I come here, 2 raised by 3, right? Odd number. So 2 raised by n minus 1 plus 2 raised by p minus 1. N is 3 minus 1, 2. P is n plus 1 by 2. So 3 plus 1 by 2, 4 by 2, 2. 2 minus 1 is 1 to 2 raised by 2 raised by 1. Answer is 4 plus 2, 6. Total GI should have been 8 by 2 raised by 3 logic. But due to symmetry, there will be some cases which will be identical, cannot be recounted, and therefore the answer will be 6. Is that absolutely okay? So yes, you should know the formula, but don't limit yourself to the formula. Limit yourself to the concept. Okay. Coming to next point. Geometrical isomers have different chemical and physical properties. I would say chemical, as far as I say, they may have different chemical behavior, usually in terms of their rate of reactions. Like one type of isomer may react faster over the other in certain reaction in terms of rate of reaction. And yes, there is a rare, or I shouldn't use the word rare, I would rather use limited number of examples where geometrical isomerism also decides which type of reaction they will participate in and which they will participate uh, or which will fail to participate. For example, so they have limited cases, but whatever they are. For example, if I have cis COH, right? This we cannot teach in 11th, but now after completion of course, you all know anhydride formation is one reaction, right? So this will form anhydride, but this cannot. Due to its position trans, it cannot have that intramolecular ring closure to form the anhydride. So such reactions can be the cases where sometimes, yes, one of the isomer is giving the reaction, other cannot give that particular reaction. Other thing I mentioned about the chemical reaction is rate of reaction. For example, cis to butene and trans to butene, if I talk of, then yes, rate of hydrogenation of cis is greater than trans, rate of hydrogenation, right? But again, this is a limited case. I cannot go for like all type of reactions. This is faster than trans. I don't know. Maybe, may not be. It depends on the reaction. It depends on the conditions. It depends on the mechanism, what type of mechanism they are following to have a particular reaction, right? So we cannot say. But yes, all I can say is chemical differences are limited. So yeah, usually not tabulated in detail. But physical differences are much pronounced, much larger, more in number. So, and I must say, always uniform. There is always such differences are always there in the two geometrical isomers. So we are referring them as general or commonly present differences in properties. So what we are talking about? Dipole moment. Okay, so dipole moment. Yes, dipole moment has nothing to do with what is cis, what is trans. It simply has to depend on the type of vectors involved. Now, dipole is fixed to be oriented from positive pole to negative pole. It is a vector quantity. If more dipoles are involved, you will have to have a dipole resultant. So after all these, I cannot say a fixed rule that always cis will have a higher dipole moment, always trans will have a higher dipole moment. That will depend on the type of groups present on that molecule. Right. For example, if this butene is considered, if butene is considered, I can say yes. If I talk of the dipole, relatively this is more electronegative. So negative pole, positive pole. This is directed this side, right? This is directed this side. And we have some resultant dipole directed this side. And as a result, I have a 0.33 dBi value for cis to butene. Whereas in case of trans, they are cancelling each other. So net dipole moment we observe is 0. And yes, we do not consider this carbon hydrogen dipole. It is like very, very less or negligible. But when these both groups having a dipole from group 2 double bond, then we had this thing. But what if one group has group 2 double bond, other has double bond to group? Now see, trans will have higher dipole moment than cis. You cannot generalize, right? So every time you have to decide this particular concept of cis high or trans high dipole moment, you immediately have to first examine the type of groups present. What type of direction of dipole individually those groups are generating, and then only you can decide whether it will have cis to be higher or trans to be higher in terms of dipole moment. Absolutely okay. Once dipole moment is decided, then all other most of the properties like boiling point and water solubility depend on dipole. Like dissolves like. So if I talk of water solubility, higher dipole moment give water, higher water solubility, right? If I talk of boiling point, then higher dipole moment will give me higher boiling point. So that way, once you are concluding that this particular isomer is having cis or trans, higher dipole moment, whichever having higher dipole moment will have higher boiling point, whichever having higher dipole moment will have higher water solubility. Automatically lesser solubility in non-polar solvents because of the fact like dissolves like. Okay, if I talk of melting point, right? Melting point, if we talk of the melting point is independent of dipole moment. It entirely depends on the type of packing that is done in solid state. So if we talk of the packing in solid state, cis, let me say cis, one side smaller groups are there. So there will always be some voids left, right? Big voids left. Like when I bring another molecule which is closer, this H is here only, na? So here a void is left. So when the packing cannot be compact, the air voids should be smaller to have a better or a compact packing. So melting point is independent of dipole moment and is always melting point of trans isomer is greater than cis isomer. Is that okay? All good? Now I am moving to these questions. You have to practice fast. Start. Count total number of geometrical isomers for the following molecules. Complete, unmute, tell me the values, please. Today I will not give you the answer key directly. I want you to unmute and tell. Yes, start. Today Shrey is not there and there was Rohit yesterday and just some moment ago Vishweshwar was there. They all are gone. I assume Mihir is in the class. CEO Vedvyas login. Where are others? No one has any answer. Okay. Girish, unmute and tell if you know about the other candidates.
I'm
Are
not
they in
sure.
the, huh?
I'm not sure about others.
They are in the class. They might be sitting in a group in a class. Is there a possibility or you're not aware?
They are not in the class, ma'am.
Okay. Okay. Bachcho. So solve these questions, unmute and tell me the answer. Start karo. Total number of GI. And when I'm saying GI, you don't have to go for counting optical isomers. As now you are aware of something called optical isomers, you may start to incorporate. No, I'm not asking.
Ma'am, first one is 2, second one is 2.
Okay. Wait. First one, he's saying 2. Okay. Others give me a thumbs up if 2 is okay for all. Okay. Fine. Second, first is 2. Okay. Second one, second
Again 2,
2.
ma'am.
Again, 2. Waiting for others' thumbs up. I'll move. Okay, good. Third. And give only one answer at a time, okay? Third. Now, Sanjay, wait for third. Let me hear it from Shiva.
Ma'am, third is 2 again.
Okay, third is 2 again as Shiva added. I guess correct answer, bete. Moving to 4. Let Girish say. Did you say anything, Girish? I could not hear.
2.
2. Okay.
I think it's 2.
But it should be 3, Girish. Check. What about my other students? Do they agree with 3? If only 3 I'm asking, then say yes. Shiva is saying yes. Girish, check this. What did you miss?
First one.
First one. So always have a sequential approach, like all in one direction. Then you go to 1 in other direction and see the cases. Then you go to 2 in other direction, and if they are repeat, let it be, like forget them and move. Okay. Let's try more. You did wrong. Continue. These are the questions 5, 6, 7, 8. Same story. Count the number of fifth again, Girish, you answer because you did wrong in fourth.
4.
Okay, let me see others. 4. Give me thumbs up if you agree, or do not agree, then don't give. No one is giving.
I cannot see it completely. Wait,
Rohit, where were you?
I've been here.
So here, other Sanjay, can you see?
Yes, ma'am.
Yeah, now I can see.
Okay. So Girish told me answer 4, and others are not supporting till now, or maybe attempting. So let's wait. What others are saying. 4 he is suggesting. Others didn't give me thumbs up for 4. Okay, Rohit approved 4. Okay, my entire class approved 4. Sanjay, Shiva, you are left. All agreed to 4. Okay, I guess everyone now. Fine. Okay, so moving to 6th. Rohit, you tell now, you were here and we were not seeing you. 6th. How many number of geometrical isomers are there?
2.
2. I guess all will be agreeing to 2. Okay, Shiva agreed. Class agreed. Fine. Move to 7th. Move to 7th. And 7th, I want answer from Shiva. I think I started from Shiva, back to Shiva. Orient. Okay. Others just keep solving, and when Shiva gives answer, we'll see.
4, ma'am.
Yeah, Shiva, you said 4.
Yeah.
Okay, let me see other students. Yes, Sanjay, what do you say? 7th?
Ma'am, I also approve with 4.
4. But beta, I got answer 3. Girish, what was your answer? 3 or 4? 2 of my candidates said 4, and I have written answer 3. Is it my error or they might have done? Should we redo?
I think it's 4 only.
So 3 of you are now at 4, so I will redo. Okay, wait.
But I think it's 3.
Rohit was in 3 suggestion. So I'll draw here. And let us see what is the repeat. All 3 on the same side. I think Rohit, we are correct, but let us draw. Ho sakta there is a possibility we might have done error. And I think all our 3 candidates, Shiva, Sanjay, and Girish, attempted by mathematics. Girish, did you draw the structures or you did math? Tell me honestly.
Uh, Ma'am, I thought you were asking about fifth question. So,
Oh, nice. 7th ka A we are.
in that case,
Hmm.
even then, I think it's 4.
Even then you think 4. Okay. So is this what your 4 is, all of you with 4? And my group of class, the one here is there. I'll tell the number, you tell in which group you are. First, 3. Oh, okay, okay. They all smart you are. Already wrote the value 3. Yes, I also think it is 3. Okay, the whole class side they are saying 3. So for these 3 people who were suggesting 4, but I think these are identical. Check. Tell Sanjay. You
Yes,
just
ma'am.
flip,
Yes, ma'am.
right?
Yes, ma'am.
Got it, Girish and Shiva?
Yes, ma'am.
Hmm. So,
Yes, ma'am.
and Shiva, how did you approach? Did you draw it or did you just possibility air may done?
Ma'am, just now I wrote it. I didn't write
No, no,
attempt
just
it.
now when I wrote
I
there,
drew
but
it, ma'am.
before you wrote, you always have to write isomers properly. Okay, then only you will get the proper. See position change. Chlorine I place like this. I think now we will have 4 because these type of cases will now be different. What do you say? You agree, na? Now if I have chlorine here instead of here, it will be different case. Check this B. This I have written 4. All of you check. And the class can enter the answer the way they did last time. That was very smooth. 3, 4, whatever you are getting, just right there. Agreed, then say yes. Disagreed, then say something. Yes, Rohit, you unmuted.
No,
What do you say?
are we going to 7B or
7B.
do
We are
we
doing
put
7B.
do we unmute an answer or do we put like the class? Like the
Unmute is also okay and class wise also okay. Whatever. I just want to know how you think. With the class, it is a problem. They cannot come everyone to the mic, so they have their code. For them, that way is fine.
4?
Yes. Yes, Rohit. Your answer is
4.
4. 4. Okay. So Rohit is suggesting 4. I got, okay, Shiva is agreeing to 4. I think if you'll draw properly, you will all will get 4. Right, Sanjay agreed. So I have only class and Girish. They show some signal and I'll move. Okay, class agreed. Girish, 4. Right. Move to this one, 8. If there are all 4 chlorine on cyclobutane.
4 again.
Okay, so answer for 8 is starting with 4. Yes, I also got 4 as I wrote here. Others, wait for a few seconds for others to join the troop and then we can go ahead. Okay, I got signal from others. And here I have to be fast. Okay, 9th and 10th. Right extreme of my screen I have tried to keep. Check yours. Can you see 9th and 10th? Or if you want, I can rewrite here. This is my 9th. PH, PH, COH and COH. And 10th is when they are placed diagonally opposite like this. Okay, now you can see properly. Do these two. One at a time, 9th alone and give me answer, then 10th alone and give me answer.
9, 4.
Okay, so I'm getting first answer 4 for this. Okay, we'll wait for others.
Ma'am, I have an answer for the 10th one, ma'am.
10th, okay, tell.
5, ma'am.
Okay, so 10th was given 5 and 9th was given 4. Let me wait for others. And Sanjay, 9th is 4?
Ma'am, checking, ma'am.
Okay, do. Then I'll show my answers. Till then, my other candidates will also do.
Ma'am, I'm getting 6, ma'am.
9th May. Okay,
6,
we'll have
yes.
options. No problem. 6 as a B option. Why not? So that way my class can write A or B in their answer or 4 or 6 in their answer, whatever they want. What happened, Girish and Shiva? I'm waiting for you to class. So kabhi bhi answer, anytime they give answer, they write and I get their answer. What about you two? Waiting for Girish and Shiva. What happened, Girish? Not getting any answer in 9 and 10?
9 I got 6.
Ma'am, 9, I think I also got 6.
Okay, so I think Rohit started with 4, but
Yeah.
he himself has jumped to 6. Okay.
10 is 5. I got 5.
10 you're going with 5. Okay. Shiva gave a thumbs up. Both Shiva, 9 and 10 both, na? 6 and 5.
Yes,
Okay.
ma'am.
Just six and 5 seems to be correct. See, 6 and 5. I also got 6 and 5. As we are talking only of geometrical till now. We are not at all talking of any of them is optical or not. Okay, so let's move further. Very famous example. How many GI for hexachlorocyclohexane? Like this hexachloro. Again, only GI. How many GI for hexachlorocyclohexane? No one speaks till I ask. Complete and then I'll ask. Yes, Sanjay, tell.
No, I have an answer, that's why.
Yeah, tell.
Ma'am, I'm getting 8, ma'am.
Okay, so same answer. Rohit and Sanjay are getting 8. Okay, so Shiva and Girish to be added. Wait,
8.
I got 8.
I think both of them just gave answer 8. Class, I assume you are also getting 8. Okay, so this is how you should get answer 8. Right, total 8 geometrical isomers we'll have. Now, this particular, where the formula fails, this you have to solve and tell. CH3, CH double bond CH, C, CH3, C, H, CH, double bond CH, CH3. Solve carefully and give me the answer. I will request to go slow and
Ma'am, I have an answer, ma'am.
no, that answer is in your memory. It is not that you solved, am I right?
No, ma'am, I immediately put it onto paper, ma'am. I saw the thing on screen, so
Okay, so what is your answer?
I'm getting 6, ma'am.
Okay, let's wait. I'll check. Others, please do.
Is it 4?
It could be 4. I'll check. I don't have in memory. Do you want me to check now or wait for others?
Saying
No, let's wait for others to join and then we'll check. Let us give them proper time to draw and analyze.
Ma'am, 6, ma'am.
Excuse me, ma'am. Ma'am,
Yes, Sanjay, you were 6. And
ma'am,
Shiva,
can I change my answer, ma'am?
okay. What do you
I'm
want
giving
now?
4, ma'am, as the answer.
Okay, so now I'm waiting only for Girish and class. Others have decided 4.
4 only, ma'am.
Okay, so Girish also added 4. Let us see. See, this is how it should be done. Is that absolutely okay? Total isomers are 4 for this particular molecule. Okay. Now here I wrote this, that CIP rule preferred Z over E. It does not mean that C, the bond is C, which I have marked here, has identical set of groups as A above and B below. So when one of them, like A is E and B is Z, right, then C could be either Z or E. But when you assign priority between A and B, right, then you have to prefer the group which is in Z configuration over the E configuration. That is why I wrote here that when you have to give their names, you have to prefer A and B's EZ. Compare. And the one in the Z configuration will be preferred over the one in the E configuration for assigning EZ to bond C. Absolutely okay. So let us move to next lecture. Now we are moving to optical isomerism. Now, first of all, what do we understand by optical isomers? So when two stereoisomers may have identical physical and chemical properties but differ from each other only with respect to their behavior towards plane polarized light. I'm not writing they are non-superimposable mirror images because that definition just limit ourselves to enantiomers. But now in phase 2, phase 3, you know that enantiomers are not just the one case which should be referred as optical isomers. Mesomers could also be optical isomers, diastereomers could also be optical isomers. So, what is the difference that we are looking for? Only their different behavior towards a plane polarized light, right? Even if one rotates a PPL and other do not rotate a PPL, still they will be referred as optical isomers of each other, right? So the difference, what is the definition of optical isomers? Such two stereoisomers which differ from each other only with respect to their behavior towards PPL are called optical isomers of each other. You know what is PPL, right? It could be polarized in one particular plane which otherwise would have been moving in infinite possible directions, right? So once I get that particular light, I pass it through a solution of the compound under study. Now, what actually happens at a very microscopic or atomic level that we will discuss. Ideally, if I talk, each molecule should be optically active. Why? Because each molecule has fast moving charged bodies inside it. All of them will have some electromagnetic field in them. So, interaction of a resultant field of a molecule with the PPL must be always there. And thus, they are all somehow having some optical activity, so should be optically active. But what happens actually is one molecule optical activity is so very less that it cannot be calculated, understood, or measured by the instruments that we use. There is always some minimum count of an instrument. That value is beyond our scope. So we always talk in terms of mole, not in one molecule. One molecule is not something that I can have for experiment. That is only ideally on paper I can talk of. So when I talk of more than one molecule, then we start talking of asymmetry. Now, why we need asymmetry, right? Why we need asymmetry, that we'll talk. First, let me read what this slide says. As per this logic, all molecule in the world should be optically active. And in fact, that is true also. But this value of rotation, like light was moving, I was observing through a lens from this side. If after placing this sample, I do not feel need to rotate this particular lens to get the maximum brightness, I'll say the compound is optically inactive. If I rotate in the right hand side direction with respect to viewer, I'll say, oh, with respect to me, I have to rotate lens to the right hand side, my right hand side. Your right hand side, if you are a viewer, then you will say this compound is dextrorotatory. If left hand, so levorotatory. So we can now in these values of rotation start talking, and for that we definitely need more than one molecule. If I take more than one molecule, either they are even or they are odd. If the molecules are superimposable, if the molecules are achiral, then what happens that one molecule's activity is cancelled by the other molecule. If they are even number of molecules, half of the molecules maybe when light is passing are in a orientation that light is rotated dextro side, then half by simple law of probability are in a orientation where the light is rotated in the anti-clockwise direction, levorotatory. So overall for me, I feel that the overall impact is cancelled and the sample is behaving optically inactive. Correct. Now, if I say, okay, there are odd number of molecules taken, then again we land to the same story that odd number means only one molecule will be in excess. Rest all will somehow have the same cancellation theory. And one molecule's activity is beyond our scope. So we consider that if the molecule can just superimpose on itself or superimpose on its mirror image by sheer rotation without any bond breakage, just moving a molecule turnaround, then that compound will not show optical activity. For example, see methane I drew here. If this arrangement, PPL coming from this direction, giving 10-degree dextro, then there will be some molecule in this arrangement. When light is moving, it was found in this arrangement and it just rotated 10-degree lever as the mirror image rotate by same value but in opposite direction. So ultimately, I feel it remain undeviated. Okay, so now what type of molecules for me? So I'll say chiral. Right? What is chiral? Such molecules which have non-superimposable mirror images are called chiral and are optically active. Now, chiral molecules are also called asymmetric. Okay, chiral molecules are also called asymmetric molecule, that is absence of symmetry elements. I'll discuss what are symmetry elements, but absence of symmetry elements is what we need. Chiral center tetrahedral atom with all 4 valencies satisfied by 4 different groups, then it is called chiral center. Molecule with only one chiral center is always optically active, but with more than one chiral center may or may not be due to the possibility of mesomerism. That we have to check. Okay. For a molecule to show chirality, it should have how many chiral carbons it should have? Yes, tell. For a molecule to show optical activity, how many chiral carbons it should have? Yes, Shiva. How many chiral carbons it should have?
1 chiral carbon.
Okay, Girish.
Think so, 0.
Why 0?
There can be some other atom, maybe.
Or you can simply say that chirality is not a property of organic molecule. It can be in coordination compounds also, Shiva.
Okay.
Right? It can be a case of allenes where there is no chiral carbon. Okay. For a molecule to show chirality, it should have minimum number of how many carbons? Already answered 0. Right? How many chiral atom? Okay, so let me continue with Girish because he opted for okay, there has to be chiral carbon 0. What about C? Chiral atom, Girish. How many chiral atoms should be there?
0.
Why 0?
You gave the example of allene.
Acha. Yes, yes. Yes, I just gave example of allene or even such type of molecules like see trans-cyclooctane. There is no chiral carbon, but it is non-superimposable. It is a chiral. Molecule should be a chiral. Right? So you are getting that chiral carbon if is there, yes, there is a possibility of optical activity. But for a molecule to be optically active, need not to be always there has to be chiral carbon. You got my point? Right? Minimum number of carbons in an alkane to make it chiral. I have already mentioned not a cycloalkane or any isotope to be used. Then you can do this type 7 for alkene and so on. Anna? Count number of chiral carbons in the following molecules. That also you can do. sp3 it has to be and all the 4 groups should be different. So in third you can see there is no chiral carbon. Right? Here also no chiral carbon because both side identical groups are there. Yes, please go through these. Nitrogen with flipping. Even it has 4 different groups is not taken into chiral atom count. When it is taken, that we'll discuss later. Okay. So see, these are some examples in cycles how to count chiral centers. You have to scan entire molecule from end to end. If there is any site which is having 4 different possible groups, you mark it as chiral and move to other site continuation. So just check all these example and approve that okay, they are correct, and then I'll move. So moving to this. Now see what is a stereo center. Till now we were talking of chiral carbon. Now I'm moving to the word stereo center. It is any atom in the molecule at which if 2 groups are exchanged and a new stereoisomer is generated. I'm saying stereoisomer. I'm not saying optical isomer. It could be geometrical isomer. Okay. Geometrical or optical. It could be sp2 or sp3. So any such atom in a molecule at which if 2 groups are exchanged and we have a new stereoisomer generated, then that center is called stereo center. Okay. For example, in butene, I will have 2 stereo center because whether I change at A, CH3 and H, I will get the cis to trans change, or I change at B, then also I'm getting the same change. So A and B will be referred as a different 2 stereo centers. Here, when there is only one chiral carbon, this. So So it has only one stereo center. When I talk of stereogenic unit, now I'm not talking of an atom, the entire unit which is responsible for generating stereoisomer. So allene unit will be taken as one unit. Biphenyl unit system will be taken as one unit, like that. Okay. One chiral center will act as a one stereogenic unit. One double bond for geometrical isomerism condition. Okay. And with our two stereo center, that entire will be taken as a one stereogenic unit because that unit is generating stereoisomerism. Okay. So for this example, I will have two stereogenic units. But if they ask how many stereo centers are there, then it is 3. Okay. Now coming to elements of symmetry. I guess all of you are aware of what is plane of symmetry. It is a hypothetical plane passing through a molecule such that one side of the plane is mirror image of other. That is called also known as reflection symmetry and represented as sigma. Center of symmetry is a point of inversion. So you have a hypothetical point within a molecule such that if you draw infinite possible straight lines through that point, then after traveling equal distances in opposite direction, for each line this condition has to be valid, you follow or you get identical atoms in opposite direction of the line. Okay, so if you have say 500 lines drawn through that center of symmetry and 499 are having the condition satisfied, one not, then also you will say the molecule is not having center of symmetry. If for plane of symmetry you have 500 planes imagined, 499 not following the plane of symmetry and one is giving that plane of symmetry thing valid, then you say, oh, the molecule is inactive, it has plane of symmetry. Quite reversal of that thing for POS and COS thing. Okay, so this is that needed for you. This is for phase 1. Axis of symmetry. Axis of symmetry is called proper axis of rotation, represented by Cn when n is something called 360 by theta. I'll refer what. So here I want to say equivalent structure like 1, 2, 2, 1. If I just rotate, I get this. Now hydrogen, if I number is 1, 2. So this will be called equivalent structure to first. If I rotate further and I get identical. So atom, same atom comes on that original atom. Same here, I know I don't mean the species, but the exact atom. Then you will use the word identical. If the same species, then you say equivalent structure. Axis should always be passed through the molecule maintaining symmetry. जिस पे आप बात कर रहे हैं, the one you're talking of symmetry. It is a hypothetical axis passing through the molecule such that when we rotate the molecule by theta degrees about this particular axis, then the new arrangement obtained is either equivalent or identical. Then the Cn is 360 by theta, where 360 by theta is this theta angle of rotation and is called order of axis. Is that okay? Now every molecule will always have C infinity, agreed, and C1. If you do not rotate, you will get C infinity. And if you have rotation done by 360 degree, you have C1. So for a molecule to be optically active, C infinity and C1 are excluded in comparing their optical activity. We say that axis of rotation is not taken to decide optical activity of a molecule, whether a compound is optically active or not. We do not decide on the basis of axis of rotation. Okay, for example, if I talk of water, it has C2 axis of symmetry. Okay, because it can have 180 से flip कर सकते. It can flip the molecule by 180 and the axis is passing through oxygen. When I talk of ammonia, if I pass an axis through nitrogen and lone pair, Then I rotate by 120, I'll get the equivalent arrangements. And so ammonia is said to have C3 axis of symmetry. Right? CO2, if we talk of C2 passing through carbon, it can have more. Agreed? The one with highest value of N is taken as CN, and the others are called subsidiary AOS. Rest all having value N less than that highest are called subsidiary AOS. Yes, there are possibility of more angles. So it is said the one with a maximum value of N is taken as principal axis of rotation. Every molecule will always have C1 and C infinity AOS irrespective of chirality. In question, when they say AOS is absent or present, then neglect C1 and C infinity. And if some other AOS is present, then you give answer. Is that absolutely okay? AOS is clear? Then we come to alternating axis of symmetry, which is called improper axis of rotation. It is also known as rotation reflection axis. Rotation reflection axis. For that, we take the original molecule. Through it, we have a axis in our imagination. Consider an axis through it. Axis. Rotate the molecule through that axis. You will get some new B arrangement. Now, this B arrangement, we keep a mirror perpendicular to the original axis of symmetry, alternating axis of symmetry that we imagined, and we have an image. So now if this C is identical or equivalent to A, then we say, okay, this molecule has improper axis of symmetry represented as Sn, where n is 360 by theta. Is that okay? Let me exemplify. See this molecule. You can see diagonally opposite ends I have kept same side. Okay. We can call it inactive by simple POS also. But I'm just using it to exemplify AAOS, alternating axis of symmetry. I'm calling AAOS. So I'm having an axis in the center, AB. I rotate by 90 degree. So 2 will come at 3, 3 will go to 4, 4 to 1, 1 to 2. So I drew this structure. This is my structure. Now as axis of rotation was vertical, the mirror will be kept horizontal. So here the mirror is kept. I took mirror image. 1, CH3 was down, so in image it will be up. Up, down, I did entire change. Now see, C is equivalent to A. Right? C is equivalent to A. So I'll say the molecule has 360 by 90, that is 4. S4 improper axis. It has S4 improper axis. Right? Should I give you some few seconds to process? If no need, give me thumbs up. If I need to wait, I'll wait. Okay, I got 1 thumbs up. Okay. Shiva and Sanjay said okay. Others. Class okay? You got that? Okay. Good. See another molecule. You just draw this, and I'm saying it has a 90-degree rotation about this. And then you can attempt on your own. This is S4 again. Okay, I'll draw it. Leave it to full screen. This has S4 alternating axis. Just draw this structure and attempt on your own. Rotate by 90 degree, take a mirror and see, is it getting the identical arrangement or equivalent? As we have said, either we need identical or we need equivalent. Drawn. Okay. So the term, if I say symmetric, then there could be alternative, any of these will be present. POS may be present, COS may be present, alternating axis of symmetry anyhow will be present, AOS will always be present, result is optically inactive. Asymmetric, then these are absent like this, and then it is active. Dissymmetric, then POS, COS, we are not talking of POS, COS, and it is active. They are basically absent. Okay. So that brings us to the closure of this particular lecture also. Tomorrow we'll start with next lecture.